What is the definition for cyclic and acyclic graph? So for cyclic graph, can I say this, that if in a graph there are two nodes such that there exists more than one path between them, two nodes such that there exists more than one path between them, then can I call my graph cyclic? Yes. Are you sure? Okay, so let us consider one example. Let us consider a undirected graph. Is this cyclic or not? Yes. Yes, it is cyclic, because if I consider any two nodes, suppose if I consider A and C, then two paths are existing, correct? This is path 1, this is path 2. But now let us take another graph. Is this cyclic? Anyone answer? Is this graph a cyclic graph or not? No. No. Because, but see, if I go by my definition, then between point nodes A and C, there is existing two paths, right? But this is not a cyclic graph. So my definition that in a graph I will be considering any two nodes such that there exists more than one path between them. This is only true for undirected graph. Is this point clear? So what will be my definition in a directed graph? So in a directed graph, if you can go from one node and come back to it with some non-empty path, then the graph is cyclic. Like this graph. It can start from node A and I can come back to node A via some non-empty path. If I travel like this, the non-empty path I am telling because someone can say that I am in node A and simply I come back to node A only, means without having any path. So that is not a cycle, right? So is this definition clear? That for a undirected graph, if you go from one node and come back to it via some non-empty path, then I will tell that a cycle exists in a directed graph. Now let us go for connected versus disconnected graph. So can anyone tell me the definition for connected versus disconnected graph?
Connected graph has only one component.
Yes, correct. So in a connected group for any two nodes, there must be a path between them. Correct? Like if I consider this, then for this component, for any two nodes, there is existing a path. But over here only, if I consider another graph, between this node and this node, is there any path between them? No, right? So it is disconnected. So you tell me, is this graph connected or disconnected? This is a connected graph or a disconnected graph?
Disconnected.
Why it is disconnected?
Because I cannot reach B from C.
Which exists so that I can reach from B to C. So this looks connected, but it is actually disconnected. And basically in directed graph, connected, disconnected, this terms you do not see also. That is why in directed graph you see the concept of strongly connected component. Have you all ever heard about strongly connected component? So later on we will be covering about this thing, strongly connected component. Okay. Basically in a directed graph, connected, disconnected does not hold any significant value. So now let us go for the last type of graph, complete graph. What is a complete graph? So in a complete graph, a graph where there is an edge between two nodes means see for this node and this node there is a edge. This node and this node there is a edge. This node and this node there is a edge. See, for every two nodes there exists an edge between them. Correct? So can anyone tell me for a connected graph what will be the number of edges? Means the minimum number of edges.
N into n minus 1 by 2.
N into n minus 1. Are you sure?
By 2 by 2.
By 2. Yes, correct. Basically, I will be choosing any two nodes and I am telling that there exists a edge. So there are n nodes, and how many ways can you choose two elements from n elements? That is nc2. So basically also, is this a connected graph or a disconnected graph? A single node means complete graph or not a complete graph? For a single node is also a complete graph, although it doesn't have any edge. So now let us go for the common terms in a graph. So one of the term is vertices and edges. Vertices, I guess you know. It basically means the node. Edges means the thing connecting two nodes. Connection between two nodes means direct connection. Okay. So now let us go for neighbors and degrees. What is neighbor and degree? Okay, so what are the neighbors of A?
B, C, E, F.
Yes. So neighbors means all nodes which are directly connected to that node. So neighbors of A is B, C, E, F. Neighbors of C,
A and D.
A and B. What is the degree of A?
4.
4. So basically degree means degree of any node X. It means how many neighbors are connected to that. Is neighbors and graphs clear? Neighbors and degrees clear? Now let us go for self loop. So suppose if there is a graph and one edge is starting from a node and also ending in that node only. So this edge I will be calling as self loop. Means there is a self loop present in the graph. Now let us discuss some important points. Path, walk and cycle. Anyone wishes to try? So a path means basically you start at a node, go to any node using valid edges, and you are basically allowed to repeat nodes and edges. So walk means you start at any node X and go to any node Y via valid edges, and even this Y can be X itself. Means you start from X and you travel a path in such a way that you reach X, X itself. That is a walk. Even if you do not move anywhere, that is also a walk. Like you started from node X and you say that you are reaching in node X only. It is basically a walk, but it is an empty walk. So via some valid edges, and you are allowed to repeat nodes. Is walk clear to everyone? Like for a graph, if I wish to go from like A to B I go, then B to C, C to D, then again I move to B, from B I go to A, then I move to C, then this is a walk. Means whatever you do on a graph, that is a work. You can repeat nodes, you can repeat edges. No restriction is there in work. Now let us go for path. In path, you start from a node X and go to a node Y. And this node Y cannot be X. And this movement obviously you will be doing via some valid edges. And over here another restriction is that you will not be repeating nodes. So over here in what the example that I gave, like I went from A to B, then B to C, C to D, then again to B, from B to A, is that a path? Yes or no?
No, because
Yes, because you are basically repeating the edges, right? So if I consider a graph like this, so what can be a valid example of path? If I go from node A to B, then I move to C, then this is a valid example of path, right? But suppose if I do this, I move from A to B, then to C, then to A, then to D. Is this a path? Yes or no?
no,
No. Why?
A is repeated twice.
Yes. So I am basically repeating a node. That is why this is not a path. Now let us go for cycle. Can anyone give me the definition of cycle by involving the term path in it? So basically a cycle is a path from X to X, and this path must contain unique nodes. Obviously a path contains unique nodes and edges. So what is the difference over here in cycle and path? In path, this point was mentioned that it cannot be X. If I start from X, then I have to move to Y, and this Y cannot be X. But in cycle, basically this Y can be X. Correct? So can anyone tell me the Venn diagram for this cycle, paths and works? How will the Venn diagram look like? Is this the correct Venn diagram? Basically, this circle means path and this means cycle. Is this a correct Venn diagram? Yes or no? So it is not a correct Venn diagram, right? Because a path and cycle cannot have intersection point. Because over here only I am neglecting these 2 points. Basically a path I go from X, I start from X and go to Y, and this Y cannot be X. But in cycle this Y can be X. So a path and a cycle must not have common point, right? So this is the incorrect Venn diagram. The correct Venn diagram is that both cycle and path are disjoint. This is cycle and this is path. Is this Venn diagram clear? So now let us do some example just to be clear that what is path and what is means basically to be clear between walk, path and cycle. So if I go from A to B, then to D and then to E, what is this? Path. This is a path. Anything else?
Walk as well.
Yes, this is a walk as well. Now let us go for another example. If I go from A, then I go to B, then I go to D, then to C, and then A, B, D, C, and then to A. So what is this? Obviously this is a walk because everything that you do on a graph is a walk. Plus what is this? A to B, then to D, then to C, and then again to A. It is also a cycle, right? Let us consider more examples. If I go from A to B, then to D, then to E, A to B, then to D, then to E, and then again to B. So what is this? We want to reflect. What is this?
It's just a walk.
Then again B. This is only a walk, right? Because one of the node is getting repeated. So this one only excludes it from both path and cycle. Now, if A to B and then to A, what is this? Means basically if I go from A to B and then again I come back to A. This is an example of what? Any one of you please reply. This is only a walk, right? Because the node is getting repeated. Correct? So, but consider this example. A, B, C, D. And over here, this is one of the edges and this is another edge. Okay. So if now I say, if I go from A to B via edge 1 and if I come from B to A via edge 2, this is an example of what?
Walk plus cycle.
Walk plus cycle, correct. Why it is not a path? It is not a path because, yes,
Node A is definitive.
yes. So, node A, I am starting from node A and then again coming back to node A. So that excludes it from path. if I go from A to B via edge 1 and if I come back to A via edge 1, then what is this work? Why now it is not a cycle? So it is not a cycle because a edge is getting repeated, right? So this thing excludes it from a cycle. So now let us go for simple definition of simple graph. So a simple graph is basically a graph with no self loop and no multiple edges between two nodes. And most of the questions in CP will be of simple graph. Can anyone tell me why most of the CP questions are based on simple graph and not on graphs with self loops and multiple edges?
Is it because of
like if anyone tells me that whether there exists a cycle or not, then you can select many number of edges between those two nodes, and then you can tell that it does not have a cycle. But if anyone else consider any other example, like any other combination of edges, then he can tell that there is a cycle. So at that time things get more complicated and confusing. That is why most of the CP questions, they will be explicitly mentioning that there is no self loop and there is no multiple edges between any two nodes. Okay, so now let us go for bridges and articulation points. So can anyone tell me what is bridges and what is articulation point? First, before bridges and articulation points, let us discuss about connected components. What is a connected component? A connected component basically means a maximal subgraph. I will be explaining the meaning of why I am writing maximal subgraph. So a maximum subgraph which are connected internally. So what is a maximal subgraph? Let us consider a graph like this. So this entire thing I am considering as a graph. So this is a subgraph, but this is not a maximal subgraph because there is a node which you can include within this subgraph. That is why we are using the word maximal. So this is a maximal subgraph. So this is one of the connected components, this is a connected component, this is a connected component, this is a connected component. Right? So what is bridge? Bridge basically means any edge whose removal will result in increase in the number of connected components. Any edge whose removal increases number of connected components. Is the definition of bridge clear? Like let us take an example. and you all will reply that whether that edge is a bridge or not. Is this edge a bridge?
No.
No.
No. This one?
No.
The blue one?
Yes.
Yes, the blue edge is a bridge. Is this one a bridge?
Yes.
Yes. This one? Yes. Right? So, why this is a bridge? Because if I remove this thing, then you can see that the number of connected components has increased, right? That is why this is a bridge. So, now bridge is done. Can you all tell me intuitively what can be articulation point?
Like removal of a node results in increase in number of forms.
Yes, exactly. Removal of node, it results in increase in number of connected components. So let us take an example. Is this node a articulation point? Just imagine that you have removed the node, and imagine that you have removed the edges connected to this node. Still, my number of connected components has not increased, right? It is still 1. Correct? So, will this be a articulation point?
No.
Is this node a articulation point?
No.
No. This one? No. Is this node a articulation point?
Yes.
Yes. This one? Is this node articulation point?
No.
No. Correct. None of these nodes are articulation points. So, you all have a basic idea about tree, right? What is a tree? If you want to define it in terms of graph or in terms of path, can anyone define a tree in terms of path?
For every pair of nodes, there exists only one path.
Yes, exactly. So in a tree, for every pair of nodes, there will exactly be one path, right? So, if we just shift our discussion little bit towards tree, then is it okay? So, for a tree, if there are n nodes, can anyone tell me how many edges will be there in a tree? The maximum number of edges that can be present if there are
N minus
1 edges. Why? Can you tell why n minus 1 edges? Because see, in a tree, I have said that between any two nodes, there is only one single path. Now, if I add one more edge to it, then that tree will turn into a graph, right? Means basically if I add one more edge, then there will exist any two nodes where you can go to both the nodes using multiple paths. Is this point clear? Yes. Yes. So in tree, what will be my articulation points? Can anyone tell me?
Any node except the leaf nodes and the root nodes.
Yes, correct. Except the root node. Are you sure? Try to remove the root node. Is my number of connected components increasing?
Not except the root node.
Yes. So any node except the leaf nodes are articulation points in a tree. Is this point clear to everyone? Now, can you find any relationship between articulation points and this bridge? Can you, yes, yes,
Like if a particular point is an articulation point, it must contain a bridge as an edge.
okay. So, how many of you agree with this point? That if a point is articulation point, then one of the edges will be a bridge. So basically you are given a statement. Yes. Now I am providing a counter example to invalidate this statement. So this is the articulation point, right? Yes. This is the articulation point, but is any of the edges connected to this articulation point a bridge? Try to remove this first edge. No, still the graph remains connected. Try to remove the second edge. Still graph remains connected. Third edge also graph remains connected. Fourth edge also graph remains connected. So none of the edges which are connected to this articulation point is a bridge, right? So this is one of the common misconception that if there is articulation point, then a bridge must exist. So this is wrong assumption. This is articulation point, but none of the edges connected to that articulation point is a bridge. Is this example clear? So now let us go for some results. In graph, can you tell some results of a graph? So let us go for first result. If there is an undirected graph where each node has degree 2, a degree at least. So suppose if there is a graph where each node is having degree at least 2, then what can you comment on this graph?
It must contain a cycle as its subset.
Yes, correct. So it must contain a cycle. Can anyone give me a proof for this? See, this proof I will be deriving from the proof of the tree. Was spelling? Okay, so let us and basically if there is more than n minus 1 edges, then the graph is bound to be cyclic. Means there will exist means in a tree I said that there will be n minus where was the tree example? Yes. So I said that there will be n minus 1 edges, and the reason is that if I add one more edge, then a cycle will be present. See, if this tree I make a complete tree, at any one edge, you will basically get a cycle, right? So from there, here what I can tell that if a graph has more than n minus 1 edges, then it is a cyclic. Correct? So, and here what does it say? That every node has degree at least 2. That means summation of degrees is greater than equals to 2n, right? Why? Because one of the edge is adding 2 degrees, right? Any one edge basically contributes to 2 degrees. That is why the summation of degrees in the entire graph is greater than equals to 2n, right? So, number of edges, it will be degree sum divided by 2, right? So, number of edges will be greater than equals to n. Yes, so is my argument true? That in this graph, the number of edges will be greater than equals to n. I proved it from the argument that sum of the degrees is greater than equals to 2n. Yes, and I have said one of the statements that if a graph has more than n minus 1 edges, then a cycle exists. So from this, can I tell that the graph will be cyclic? Is this proof clear to everyone? Or anyone has any doubt? Yes. So this was a kind of mathematical proof. Now let us first try to prove it with a little bit intuition. So I will be using the longest path argument. See, if there is a graph, it is sure that a longest path will exist in a graph, right? Yes. So consider a graph in which this is the longest path. And from any node, there are multiple nodes going to sideways, but I know that this is the longest path. So, if this is the longest path, but I am telling that, okay, so don't give these two nodes as edges, because if you give this n points more edges, then basically your longest path can increase, right? So these two nodes are not having any more edges connected to it. This is the longest path, but I am telling that in my graph there will be at least degree 2 for every node, right? But the starting node and the ending node, it is not having degree 2, correct? So if I wish to make it degree 2, I have to add one more edge to the starting node and the ending node. Yes. But if I add one more edge to it, then, and if I add a node, means suppose there was any other component of the graph and I added a edge. So is my longest path increasing? Correct? But my longest path must not increase because I have already said that this is my longest path. So to validate that my graph will not be having a longest path, means this will only be the longest path, and I have to also make the degree of the starting node and the ending node as 2. So this argument can only be valid if any of the nodes in between this longest path is connected to the last and the right node, right? Then only this argument is valid that this is the longest path and the number of degrees of every node is at least 2. Correct? From this means from your starting node and your ending node, one of the edge must come back to one of the nodes already present in this path. That means a cycle must exist. Yes. Over here, 2 cycles is existing. But if you add like this, then 1 cycle will exist. Correct? Is this argument clear to everyone? How I am proving it with the longest path? Anyone has any doubt in this thing? Okay, so
Sir, can you repeat the second point?
second point, okay. Longest path, right? Is this point clear? That if there is a graph, a longest path must exist in a graph. Yes or no?
Yes.
Yes. So, suppose this is a graph and in between this and this thing I am telling as the longest path. From this node I go to this node, I go to this node, I go to this node, I go to this node. This is the longest path. Okay. And over here in between these nodes, they may be connected to other nodes. I do not care. But the starting node and the ending node must not be connected to any other node. Correct? Because if I connect to any other node, then my longest path is increasing, right? So, for now, the starting node and the ending node is having only one edge. But what is my question? That an undirected graph where each node has degree at least 2. But my starting node and my ending node is not having degree 2. Now they are only having degree 1. Right? Till this much is it clear? Yes. So, if I wish to make it degree 2, and if suppose this is any other part of the graph like this, and any other component is there like this, if I join this, then your is my this as the longest path still? No, right? My longest path is increasing. Correct? Yes. Even if this I connect to this node, still my longest path is increasing, right?
Yes.
Yes. So I cannot connect it with any subnode. So if I want to make the degree as 2, with which node should I connect? Such that this remains as my longest node and my condition that starting and ending nodes will have degree 2 will be valid. If I add this edge, then is this still the longest path? Yes or no?
Yes.
Yes. And now the ending node is having degree 2, right? Similarly, if here I connect it to any other edge, then my starting node is having degree 2. Also, I can connect the starting nodes and ending nodes also. Basically, to make the degree as 2, I have to connect the starting node and the ending node with any other node present in between the longest path. Correct? Yes or no?
Yes.
Yes. So if I connect to any other node present in the longest path, that means only I will get a cycle. Right? There is a longest path, and with the longest path I am connecting it with any other node present in the longest path. Then only see over here there is a cycle. Right? So now is it clear that how we are proving it with the longest path argument? So let us move forward. So can anyone comment on the sum of degrees, on the parity of sum of degrees? Will it be even, will it be odd, or will it be even and odd? Sum of degrees is, yes, sum of degrees is always even. Why? Because one edge will be contributing 2 degrees, right? So sum of degrees is equals to 2 into edges, correct? So edges can be odd or even, but 2 into edges will always be even. That is why sum of degrees will always be even. Can anyone comment on the number of nodes with odd degrees? Number of nodes with odd degrees, will it be odd even, or can it be even or odd as well? This also needs to be even, right? Yes, correct. Number of nodes with odd degrees also needs to be even. Suppose, for example, let us consider some node. Suppose a graph is made between them. I know that suppose the degree of this is 2, degree of this is 3, degree of this is 4, 4, 5, 6, 7, 8, 9, and degree of this is 6. This is not valid graph, right? Because I have already said that the sum of degrees will be even. Is the sum of degrees even? No, right? So any one node must be present whose degree is odd. That means even number of odd degrees must be present, so that if you do the sum, then you get an even answer. It is just following the logic that even plus even is even, and even plus odd is equals to odd number, but odd plus odd is equals to an even number. This logic is being followed over here. Is this point clear to everyone? So let us go for storing a graph. How many ways are there to store a graph? First, let's go for adjacency matrix. So, how do you store a graph in an adjacency matrix? Basically, you create, if there are n nodes, then you create 1, 3, 5. You create a n cross n matrix. And basically, if a edge is existing between any two nodes, then you simply mark it as 1, and if edge is not existing, then you mark it as 0. Like if this is the graph 1, 2, 3, 4, 5. So 1 to 2, a edge is existing, so I mark it as 1. Even 2 to 1, a edge is existing because it is an undirected graph. So I mark this as 1. 1 to 5, 1 to 5, 5 to 1 also, 2 to 3, 2 to 3, and 3 to 1 also, 4 to 5, 4 to 5, and 5 to 4 also. Am I missing any edge? 1, 2, 3, 4, 5, 6, 6 into 6. And rest all are 0. So for undirected graph, looking at the adjacency matrix, can you comment anything from the adjacency matrix? Can anyone make any observation on an adjacency matrix of undirected graph?
Matrix of ij must be equal to matrix of ji.
Yes, correct. So it is symmetric, right? Is this point clear? That in an undirected graph, the adjacency matrix must be a symmetric matrix. So, in competitive programming, what do you think? Is storing a graph in an adjacency matrix a good way to store a graph?
No.
No, or yes? Your voice was not clear?
No.
No. Why?
Like if the nodes values are present like 1, 2, and 100, so we have to make.
No. Yes. Yes.
Like if the nodes are present values such as 4, 5, 6, and 100, so we have to make a matrix of size 100. So there would be lots of wastage of space.
Yes. So, but this basically depends. In CP, yes, mostly you will not be storing it in an adjacency matrix, but you need to understand the trade-off. So, for finding the number of neighbors of any node in an adjacency matrix, what will be my time complexity? If I tell you that, tell me the neighbors of 2, if I have given you the adjacency matrix, then what will be the time complexity? Big O of n, right? Big O of n, because for these two nodes, node 2 you have to traverse this entire length. It is having 1, so 3 is a neighbor, right? So the number of neighbors I can find it in big O of n. Now, if I tell you, is there an edge present between x to y? Using an adjacency matrix, what will be your time complexity? Big O of 1, right? Is there an edge existing between 2 and 3? You will simply write adj of 2 and 3. Correct. 2 and 3, you are saying that there is 1, yes. So, edge exists between 2 and 3. 2 and 4, adj of 2 and 4, 0. So, no edge exists between 2 and 4. What is the space required to store an adjacency matrix? Big O of n square, right? Removing an edge, what is the time complexity? Big O of 1, right? Because removing an edge means I will be making a 1 as 0. So simply I can do like adj of u comma v is equals to 0. My edge is removed. Adding an edge, this is also a big O of 1 operation, right? So now let us go for adjacency list with vectors. So in this thing, you will be having a vector of vectors. And this outer vector will be having a size fixed as n, which will be equal to the number of nodes. But the inner vector, that can be of variable size. And it will basically be storing the neighbors, like adj of I, it will be storing all neighbors of I, correct? Like if I consider a graph like this, so will be storing its neighbor 2 and 3. 2 will be storing its neighbor 1 and 5. 3 will be storing its neighbor 1 and 4, like this way. What about the same thing? If I wish to find the number of neighbors of a particular node, then what will be my time complexity? Can anyone tell? Your voice was not audible.
Big O of 1.
Big of 1, yes. I will only be doing adj of I dot size, right? If I wish to know whether an edge exists between x and y, then what will be my time complexity over here?
Big O of n.
Big O of n. Space which it is taking, big O of edges, right? I am storing all the edges. In a undirected graph, you can tell big O of 2 cross edges like that. But the main thing, it will be storing edges. So space, it will be consuming big O of edges. Removing an edge, it will take big O of n, right? You have to find the edge and then you have to remove the edge. Adding an edge, it will take big O of 1 operation, right? Simply you will be doing pushback operation. So can you from now only see the trade-off? Like space was n square, over here space is big O of edges. In the previous thing, if whether a edge exists between x and y, you can find it in big O of 1, but with vector of vectoring, you are finding it in big O of n, right? So this is the trade-off, and this thing you have to keep in mind during CP. That what data structure you must use to store the graph in such a way that you give your answer in the most optimal way. Another way to store the graph is adjacency list using set. So this is like I will be storing vector of set of int. Over there I was storing it in vector of int. Over here I will be storing it in vector of set of int. So what advantage will I get? Number of neighbors, here also big O of 1 operation. Is there a edge between x to y? In vector of vectoring, I was finding it in big O of n. Over here, what will be my time complexity?
Log n.
Log n. Exactly. Space, it will be same. Big O of edges. Removing an edge, over there it was big O of n. Over here, what will be my time complexity? Log n, right? And adding a edge, in the previous case it was big O of 1. Over here, what is my time complexity to add a edge? Big O of log n, right? Similar to insertion in a equals to 10 to the power 5. Number of nodes is 10 to the power 5, number of edges is 10 to the power 5. Then can you store it in a matrix? So which data structure you must use? Can you use n is equal to 10 to the power 5 and n is equal to 10 to the power 5 in a matrix? No, right? Because space will be n square. That much space you are not having. Vector and set you can use. Suppose n is equal to 10 to the power 3 and m is equal to 10 to the power 5. And over here I tell you that the operation which the question is asking you to do is adding edges and removing edges. So over here, which thing will you be using?
Matrix.
Matrix, right? Because now space is not the problem. Number of nodes is 10 to the power 3. So I can go for 10 to the power 6 space. And adding and removal in a matrix, it is very easy compared to a vector or a vector of set. And the question says to add edges and find the number of neighbors dynamically. Then what you will be using? You will be using vector of vector, right? Because space will not be an issue over here if you use vector of vector. And basically you are adding a edge. Adding a edge in a vector of vector, it is big O of 1 operation. In a vector of set, it is a big O of n operation. Okay. So till this much, is everything clear? So this was all about the introduction of graph. Now let us go for the traversal technique. So what are the traversal techniques in a graph? Can anyone tell me any of the traversal techniques that you know?
BFS and DBS. DFS.
Yes. BFS and DFS. So first, let us start with DFS. So what is the DFS? DFS basically means that for a particular node, I will go as deep as possible and then backtrack. Right. So first of all, can anyone tell me, has anyone solved any question of tree and graph in CP? Have you all solved any graph question in CP? Any graph or tree question in CP? Yes or no?
Not really.
Okay. So then I will be explaining that point. So if I start a DFS from A, then from A I will go to B, from B I will go to F. Basically, in a DFS, I will be, for a particular node, I will be going as deep as possible. From A, I saw that B is there. Even I could go to G also first. It doesn't matter. From A, I move to B. From B, I move to F. From F, I move to D. From D, if I move to C. From C, I can move nowhere. So I will be backtracking. From D, can I move to anywhere else? Yes, I can move to E. From E, can I move to anyone else? Yes, I can move to H. From H, can I move to anywhere else? Yes, I can move to G. From G, can I move to anywhere else? No. Then I backtrack. You backtrack from E to G, then from D to F, D to F, and from F to F. Is this traversal technique clear? That's how I am doing DFS traversal. For a particular node, I am going as deep as possible. Now, let us understand the DFS traversal in a tree. And then let us try to draw a comparison between how a DFS in tree is different from a DFS in a graph. So, DFS in a tree, from this node I move to this node, then I move to this node, then I backtrack, then I move to this node, then I move to this node, then I move to this node, then I move to this node. After that I move to this node, this, and this. So, with this traversal, can I tell this statement that for a DFS on tree, any new node that you visit is a child of the previous node? Any new node that you visit is child of previous node. Is this thing true in tree? See, any new node that you are visiting is a child of the previous node, right? Is this point clear? But is this thing true in a graph? This thing is not true in a graph, right? Because by doing DFS traversal, in a tree also, when you do a DFS traversal, you will be always going away from the root, right? But in a graph, this is not the case. You can come closer to the source node itself. See, from A, my last traversal was on G. Instead of going away from the source node, I came closer to the source node. So in a graph, you can even, while doing a DFS traversal, you can come closer to the source node. Correct? If suppose this is the tree and if I start a DFS traversal over here, like if I visit this node, then I am totally sure that this part will be unvisited, yes or no? Can anyone confirm that if I start a DFS traversal on the left side, then I am completely sure that all the nodes on the right side will be unvisited? Correct?
Yes.
Yes. But is this the case in graph? No. Like on a tree only, let me make a graph. So to make a graph, I will not do anything. I will just be adding an edge. So if I add an edge, now is this point valid? It can happen that over here I move to this node, then I move to this node, and from this node I completed the entire DFS traversal, right? So this point is not valid in a graph. but it is valid in a tree. That is why in a tree you do not need a visited array. But in a graph you need a visited array so that you do not revisit your node. Is this logic that why a visited array is needed clear in a graph and why a visited array is not needed in a tree?
Yes, clear.
Yes. So, yes, anyone has any doubt? No. Okay. So, the code for DFS, do you all know? Or let us write it only. So, how can you input in a graph? Number of edges will be n and m. You will be inputting n and m. After that, in CP, your statement will be given like there exist n lines, each containing edges from u to v. So basically, I will be using vector of vector int. This will be named as edges of size n. There are n lines, so int I is equals to 0 and it will be going up to n. Each line will contain two integers, so u and v representing the edge between the two nodes. So I will be taking input of u and v. After that, I will be doing u minus minus and v minus minus in this case. Why? Because over here I am considering zero index graph. Like my first node is a zero node. Okay, so that is why I am doing minus minus. In most of the CP problems, it will be one based indexing. If you wish, you can bring it to zero based indexing and do your entire problem. Okay. So after that, edges of u dot pushback v, and if it is an undirected graph, then also do edges of v dot pushback u. Is this clear how you will be taking input in a graph? Now, how you will be doing DFS traversal? So in my main function only, I have to keep visited array. So vector of bool of visited, its size will be n and it will be containing false, representing all are visited. And then vector of to store the entire graph means if I do a DFS traversal, then I will be keeping vector of in DFS traversal, and then basically I will be doing a DFS traversal on source, edges, means you pass everything. DFS traversal, visited array also. Also keep the source as 0 for now. So how will my DFS algorithm look like? So my current node I am representing as NN. After that, first I will be pushing it into DFS traversal dot pushback NN. After that, visited I will be marking as true for the particular node. Correct? Just a second. Visited of NN I will be marking true, means this node is visited. After that, I will be traversing all the nodes and calling the DFS function of v of edges of NN. This will be giving me the neighbor, and if this is not visited, then only I will be calling the DFS function. DFS of now it will be v, and you pass all the other parameters that you are having. Is the DFS code clear? That basically you start a DFS, you mark the node as visited, you do anything on that node. After that, you go to all the edges, all the neighbors of that node, and if that neighbor is not visited, then you again call the DFS function. So, what is the time complexity for this code? We go n plus m, right? Basically, you are visiting all the nodes and all the edges once. That is why it is big O of n plus m. But what is the drawback of DFS? With DFS, can I solve shortest distance problem? Yes or no? Anyone please answer? Like with DFS, I cannot solve a shortest path problem, right? So, for this reason, I need DFS traverser. So, how is a DFS traversal done? In DFS traversal, like I will be traversing level wise. So, suppose there is a graph. So, let us mark the node. In DFS, we follow one of the algorithm that if node U comes before node V in BFS order, then children of U must come before V in BFS order. Like this is the node, I start a traversal, BFS traversal, first I visit B. From B I cannot visit the children of B. I must first visit the children of A first, and then I will go for traversing the children of B. Like this is node U, this is node V. What I am telling, if node U is coming before node V, right? Then in BFS order, children of U must come before children of V. So I cannot visit children of V now. I have to first visit the children of U first. So children of A I visited, that is C. After that, I will be visiting children of B, E, and then I will be visiting children of C, that is D. From E, I will be visiting children of E first, that is I and F, and then from D, I will be visiting children of B first, that is G. Then from E, I will be visiting the children of I first. Correct? So is this point clear? That if node U comes before V, then I must use to follow this property that who comes first he will be visited, and then everyone else will be visited. Which data structure can you use? Q, right? Yes. So is this point clear why in a BFS we use a Q? We use the Q in BFS for this logic, that if a node U comes before V, then its children will be traversed first, and then the other children will be traversed. Correct? So now the code for BFS. So basically, you will be having a source node as 0. Here also you need to maintain a vector of pool of visitors n comma false, q of int of q. Also in BFS, can you notice this thing? I am always going away from the source node, right? Yes, but this thing was not true in DFS. For this reason, DFS is used for shortest path problem. Like if you start from a source node to a particular node, BFS will give you the shortest path instead of DFS. So, visited of source will be marked as true because now you will be pushing your source node in your queue, and after that, while not q dot empty, you basically pop out the front element in the queue. After that, do anything with this node, whatever thing is given in the question, and then you push back all the neighbors of this node, the edges of top, and basically you mark that node as visited, whichever neighbor you will be pushing into the queue, and then basically push it into the queue. Is the code for BFS clear to everyone? So a BFS will be giving you the shortest path in a unweighted undirected graph. In a weighted undirected graph, how you will be getting the shortest path? Can anyone tell me? You will be using Dijkstra, right? If the graph is weighted. Correct? So now, by traversal technique, let us do some problems. Your first problem is that find all the edges in a component, all the nodes in a component. So how you will be doing this? Like if you have a graph as like this, so here two components are present, right? One of the component is 3, 4, 5, 6, 7. Another component is 1, 2, 8, 9, 10. So how you will be printing this thing?
We can run either DFS or BFS on both the components.
Yes, correct. So I will basically be doing I is equals to 0 up to n. If it is not visited, then I will be having a vector of components, and basically I will be calling a DFS or a BFS, it doesn't matter, with node and component, right? And then in a global, you can have a vector in, and this component that you get, you can basically push back into the answer. Is this thing clear? After that, if you go for other questions, like if you want to find the maximum area in a maximum area of island in a binary matrix, that also you can do, right? With traversal, like 0, 0, 1, 1, 1, 0, 0, 0, 1, 1, 1, 0, 0. So it is containing 2 islands, right? So this also you can do using BFS traversal. Over here, what will be your graph? Your graph will basically be this edges, all edges, right? Every node is connected to everyone. Can you code this thing up by yourself? Basically, whenever you find the one which is not visited, then you visit everything connected to the one, and that is one of your islands. And like that way, you can approach the question. After that, let us suppose you are given a matrix of all zeros, and only one is present, and this one is representing a rotten orange, and only one will be present, means only one rotten orange is present. So I need to find that how much minimum time is needed to rot all the oranges, such that in 1 second a rotten orange will make its adjacent oranges rotten. In the other second, the adjacent orange will make other oranges rotten. So which traversal technique will you use? BFS, yes, for minimum time. But for this question, do you need to use BFS, or can you solve it using any other approach also? Only one orange is rotten. See, basically in this question, I don't need any traversal technique. I know that the maximum time which orange will take to rot will be the oranges on the edges, right? They will be taking the maximum time to rot. Means any one of the orange on the edge will take maximum time to rot. I have the index of 1. Suppose this is x1 and y1. That is the index of 1. I know all the indexes of everyone on the edges, right? Suppose an index on the edge is xe and ye. So what is the distance between xe and ye? It is mod of x1 minus xe plus mod of y1 minus y, right? So I will be traversing on all the edges. I will be finding the maximum distance of this, and this will be my answer. Is this logic clear? That over here we do not need like any traversal technique. Although BFS is an approach to solve this question. Now, if I tell you that instead of one rotten orange, there are multiple rotten oranges, then how will you solve? Can anyone tell? Instead of one rotten orange, there are multiple rotten oranges, and I need you to find the minimum time to rot all the oranges. Then what will you do to solve this question? One of the approaches is that for every rotten orange, you will be doing a BFS traversal, and you will be finding out the maximum, means the time it is taking to rot all the oranges. Like for every rotten orange, uh, rotten orange, do BFS, find time for every rotten orange, and in a global you maintain a maximum, and the maximum of all this time will be your and basically no, you have to find the minimum, right? The minimum of all this time will be your answer, right? Like for 1, I will be from 1 I will start a BFS traversal. I will rot all the oranges, and suppose if this time taken is 3 seconds. After that, from this one I will start, and then I will be rotting all the oranges, and this time suppose taken is 5 seconds. Then obviously 3 seconds is better than 5 seconds. Like this rotten orange can rot the entire basket in 3 seconds. So minimum time is 3. So from there I have to find the minimum time of all the time. Another approach can be multi-source DFS. And what is the time complexity of this? It is obviously big of number of rotten oranges into n square, right? Yes. So this is obviously in most of the CP problems it will give you clearly. So to optimize it, see now this is a really beautiful technique. One of the techniques that most of the people you will see following is that if there are multiple sources, then all the sources they will push back into the BFS. Like I will be doing Q dot pushback, coordinates of rotten orange 1, Q dot pushback, coordinates of rotten orange 2, and so on. And after that I will be doing my BFS traversal. Correct? So in this way also I will be getting the minimum time in which I can rot all the oranges. Basically, if you are having multiple sources, then all the sources you push back into your queue and then start your BFS traversal. But this approach is not so intuitive. Now see approach 3, how can we do? Suppose if I am having a graph, this is a graph, and suppose my orange, this orange is rotten, this orange is rotten, this orange is rotten. Okay. Now I am telling that I will create a dummy node joining all the rotten oranges. And then from the dummy node I will be doing my BFS traversal. So if from the dummy node I do BFS traversal, then this distance is 1, this distance is 2, this distance is 3, and this distance is 4, right? So I have started my BFS from one node only, correct? From my dummy node. And I have populated my distance array. And now I am telling that since I have added a dummy node, I will be removing this dummy node. So if I remove this dummy node, I must decrease all the distances by 1, right? So all the distances will be decreased by 1. And I will be finding the minimum in the distance array. Is this dummy node concept clear? Like if you are having multiple sources, join them with add one edge with a dummy node, and then you do the BFS traversal from a dummy node. And then after you have done the BFS traversal, you assume that you are removing the dummy node. So all the distances must decrease by 1. That is why all the distances I will do as -1, and then your traversal is done. Is this Concept clear to everyone? The dummy node approach, how can we use dummy node to solve multiple source BFS problem? Okay, so now let us see one more thing in BFS and DFS. Is my screen visible?
Yes. See, in sometimes you have to also do path traversal, right? Means find the path. Correct? So in path, what you will be doing, you will be creating a parent vector, which will be storing your parent in the BFS traversal. See over here, we have created a parent vector. P is the parent vector. Parent of source will obviously be -1 because source is not having any parent. After that, while doing a BFS traversal, whichever neighbor I will visit, that means neighbor's parent. Over here, U is the neighbor. Okay. So, U's parent will be your V, right? From where you are visiting. You are going from V to U. So, U's parent is V. Is this clear how you are storing the parent array? And now if you have to print path, so basically I will be starting from my end node. U is my end node, and then I will be going up to -1. That is the parent of the source node, and then for U I will be pushing for V I will be pushing it back into the path, and then I will be moving to the parent of V. See, that is why it is written V is equals to parent of V. And this I will continue till I do not get a -1. Is this concept clear of path?
Yes.
Okay. So, let us solve some few more questions.
Okay, so after this, after this question, we'll move into topo third part. So थोड़ा उसका देख लेना.
Okay. Okay. So, let us see some few questions. So, this question just says that you have to count the number of rooms. Hash represent words, dot represent room. So how you will be doing this? You will be simply doing a BFS or BFS traversal, right? Wherever you see a dot which is not visited, you increase your count and just do a BFS or BFS traversal. So that is only the code. Like I have maintained a visited array. I am checking for all the nodes. If this is a wall, then I am continuing. Else, if it is a dot and already visited, I am continuing. The code is not visible. Achha. Is it visible now?
Yes.
Wait a second. Let me, instead of sharing tab, let me share my entire screen. So, if it is a wall, that means if it is a hash, then I am continuing. If it is a dot and if it is already visited, then I am continuing because I have already visited it. Else, it is a dot and it is not visited. That means it is a new room, right? That is why I am increasing my count and then I am doing a DFS traversal. And after that, I am printing the count.
Is this problem clear? For this problem, you are given a map, your path. It is a path finding problem. Basically, you will be starting from A and then you will be going to B, and basically you have to find the shortest path. So I will be using a BFS traverser, and with this I will be using path, right? So if you see the code, so I have done a BFS traversal. With BFS traversal, I have maintained a parent array, PAR, yes. So over here, I have stored the parent. After that, I have found the path in which we are moving, and then basically over here I have found the path. And like I have made up down, how you will do by using the x difference and y difference. Like if x difference is 0 and y difference is 1, that means you are moving right. In that way, we have stored the path over here. So this was the second problem, building road. And let us go for a multi-source BFS problem like mentioned. So there are n cities, and you have to find the minimum number of roads required such that all the cities are connected. So this was like you have multiple components, and you have to find the minimum number of nodes required such that all components are connected. So basically it means that you have to only output one of the nodes of every component.
Yeah,
right?
can you discuss the question after the toposort topic is taught?
Okay, so
Okay, now
let
so
us,
toposort will be continued. Then again we'll discuss questions.
okay.
So let me share my screen for the toposort. Is it visible?
Yes.
So toposort is basically hearing the term sorting, what do you understand? Like placing numbers one after the other depending on some condition, right? So normal sorting, what we do, we compare them according to which is bigger or smaller. Normally whatever sorting you have learned till now. But here in topological sorting, our main concern is about the order in which the elements appear in the graph. And you have already learned about what is the directed acyclic graph. So this topological sorting is possible only if the graph is a DAG. And if it's not a DAG, then we can check that also, whether a graph is a DAG or not. Is whether a cycle is present in the graph through topological sorting. So here you can see a simple example. So this is a DAG which is given to you, and this is the topologically sorted graph. See, after 0, means 0 and 6 are here, and then we have 1. From 6, 1 is connected. So after 6, we can have 1. Then from 1, we have 2. So 1 and 2 will have a connection. So 2 will always appear after 1, never before 1. So that is the sorting criteria over here, that since 2 is appearing after 1, means 2 is connected to 1, so 2 will appear always after 1, never before 1. Similarly, you can see that this 3 is appearing after 2. Why? Because 3 is connected to 2. Now, to get a better understanding of this, I will show you a visualization. Can you see the screen? I've changed it.
Yes.
Yeah. So there are two versions. Observe it carefully, how it is going. This is the DFS version. You have already learned what is the DFS. So observe it, how we are getting the nodes over here. So what does a DFS actually do? It means traverses the elements as deep as it can go inside the graph. So like if we are starting from 0, we will go to 1. Let me replay it, then it will be better to understand. See, we are starting from 0, we are going to 1 because 1 is its neighbor. Then to the neighbor of 1. Then again to the neighbor of 2. Then to 4 because it's a neighbor of 3. And now we can understand the order over here. Then 5 is the neighbor of 2. Similarly, this 1 was left, so this 3 is a neighbor of 1. Next 2 is a neighbor of 0, and this is another connected component. This is one connected component, and this is another one. So like this, we can give the order in which the elements are appearing according to their connections. Now, so I think this you have understood through the visualization. So we will just go through the code once, how we are using DFS to get the topo sort of the graph. See, first we'll read how is it happening. First we'll initialize the visited array, like similar to what happens in a DFS. The visited array is needed to mark which nodes are visited and not. Then for each unvisited vertex, we will call the DFS function. Now mark the current node as visited and recursively call DFS for all its unvisited adjacent vertices. This is completely similar to DFS. Now, after exploring all the neighbors, push the current node onto the stack. So we are using a stack to maintain the order in which we are traversing the nodes. And then we will pop out from the stack and we'll get the topological order. After all the vertices are processed, we'll pop the elements from the stack to get the order. Now, let's look at the code once. See, this is the adjacency list that we have constructed over here. Next, the topo, this is completely same to DFS, only we have introduced the stack portion to track which elements are coming, right? Because from the stack only we can retrieve the topological sort. Now this is the function where we are where we'll get the sorted order actually. See, this is the adjacency list, and then this is the visited array. We are defining it. We have defined the stack. Next, if it is not visited, only then we'll call the topo DFS function. This is completely similar to DFS. Only one change we have made. We have introduced the stack thing. Now this is the result, and we are simply pushing. We are popping elements from stack and pushing it onto the result, and we'll finally give the result out. That's the topo sort. I believe this is clear.
Yes.
Okay, so this is the simple version using DFS. We just tweaked DFS. Now there is another dedicated algo for this. It is Kahn's algorithm. Here you need to know one thing: in degree and out degree. In degree is basically the number of edges that are directed towards a particular node. See, here we have two edges incoming to 0, right? So in degree of 0 will be 2, means this node will be 2. Similarly, in 2 you can see there is one incoming edge and one outgoing edge. So this in degree is 1, out degree is 1. So 2's in degree is 1. Similarly, 1's in degree is 1. So why do I need in degree, out degree? In Kahn's algorithm, we basically first put into the queue those nodes which have in degree 0. And then we process it. I will show you the visualization for this too. See, the Kahn's algorithm, this is a BFS version. See, this in degree is 0 of this node. Wait, let me stop it. Yeah. In degree of 0th node and 7th node is 0. Why? Because there is no edge which is incoming to this node. Only edges are outgoing from this node. So this has in degree 0, this also has in degree 0. So I will first push these two nodes in the queue and then I'll process the algorithm from here. So next 1 and then 2. I'll show you the algorithm after the visualization. Okay, so this is our topo sort that we got. Means the labeling shows the order in which the nodes will appear in our topological sort, final. Okay, let's look at the algorithm first. First, we'll add all nodes with in degree 0 to a queue. This is very similar to a BFS. Means it's actually tweaking the BFS algorithm. So the nodes which have in degree 0, we will push them into a queue. Then while the queue is not empty, means there is at least one node in the graph which has in degree 0. We will remove that node from the queue, and for each outgoing edge from the removed node, decrement the in degree of the destination node by 1. What does this mean? That means if you remove the node which has in degree 0, then the destination node means that in degree 0 means what? Look here. This is the 0th node, this is in degree 0. And this edge is going out from 0 to 1. That is why 1 has in degree 1. So when you're removing this node, you're basically removing this edge also. So you should decrement the in degree of 1 by 1. Means you're just subtracting 1 from the in degree value. So if I just remove this 0th node, then you can imagine that this 1 will not have this edge going into it. So the in degree of 1 will become 0. So next in our queue, the node which we'll have is 1. So this is the meaning of this line, that for each outgoing edge from the removed node, decrement the in degree of the destination node. Destination node is which one here? 1, because it's going from 0 to 1, this arrow, that is this edge. So the destination node's in degree will be decreased by 1. If the in degree of the destination node becomes 0, then add it to the queue. That is what was happening over here. In 1, we had in degree 1, but when we removed 0, then this edge got removed, so its in degree will become 0. So we'll push it into the queue. If the queue is empty and there are still nodes in the graph, then the graph contains a cycle and cannot be topologically sorted. So if there is in the first only I told you that toposort is only applicable for, means you will get a toposort only if it is a DAG, that is a directed acyclic graph. If you have a cycle, then the toposort means the algorithm will run, but there will be nodes which will be untouched. Means those the number of elements in your toposort and the number of nodes in your graph will not be same. The number of nodes in the toposort will be less than the number of nodes in the graph. That shows that the graph is cyclic. Now the nodes in the queue represent the topological order of the graph. To demonstrate this, we have this code. See, this is again the adjacency list. Now in the topological sort, now this is very much similar to a BFS algorithm. In the adjacency list, you put this. Now in degree is those nodes which have, first we are assigning the in degree actually. For auto ID and adjacency I means if there is a node, this 0 and 1, consider these two nodes. The adjacency list of 0 will contain 1, right? So the in degree of 1 will be increased by 1. That is what this code is doing over here. For all the neighbors of I, neighbors are represented by IT over here, their in degree must be increased by 1. Now this is the queue where you will push all those nodes which have in degree 0. Now this is the result vector that you are defining to store your toposort. While this queue is not empty, you will push out a node from the queue, that is the queue.front. And you pop it from the queue, you no longer need that node. Then result the pushback node. Like in the first, this 0 was there, right, which has in degree 0. So this was in the queue initially. So when you are saying that while queue is not empty, then you will pop this out from the queue and push it into the result vector. And then again, the same things, like it's for its neighbor, you continue the process. Decrease the in degree of its neighbor, because I explained this already. Because of this arrow, when you are removing this in degree of this node will decrease. So same thing is happening over here again. You will loop it until the queue becomes empty. And this one is important. If result of size is not equal to V, what is V? The number of nodes in your original graph. If the number of nodes in your toposort is not equal to the number of nodes in original graph, that means the graph contains a cycle. Otherwise, the result is storing your toposort. A quick question on this, it's completely similar to the thing which you learned just now. The question says that you have, is there a total of num courses that you have to take, and the courses are labeled from 0 to num courses minus 1. Now there are prerequisites for the course, and how are they labeled? Like AI, BI means you must take course BI if you want to take course AI. That means BI must come before AI. So that is the inherent order that you need to present. So this gives the idea that you must use toposort to solve this question, because this idea of coming before and after is coming over here. So these are some examples to illustrate what the problem says. Like, let's see this one. Dumb courses is 4 and prerequisites is 1, 0, 2, 0, 3, 1 and 3, 2. Means for taking course 0, you must take course 1. For taking course 0, you must take course 2. And for taking course 1, you must take 3. Similarly, for taking 2, you must take 3. So 0 to 1 must appear before. Why? Because 0 must be taken before 1. Then 0 must be taken before 2. So you see, this 2 and 1 are after 0. Then 2 must be taken after 3. So 2 is first and then 3. So this is just the code that we just did, the same code, because this is an application of toposort. So the code remains quite the same. This is find order. This is actually a leak code problem. So this is the function name in num courses and prerequisites is the vector. This is actually the adjacency list kind of. So here you are pushing back the neighbors and you are calculating the in degrees of the nodes. Now here is the queue. In the queue, we need to push those nodes whose in degree is 0. We did that here. Now the same thing again. This is the answer, the topo sort vector which we have defined. Now while it is not empty, then we'll push the node into our answer, that is the topo. And then for each of the neighbors, we'll do the same process. As we visit the neighbor, then its neighbor's in degree will decrease. And if it decreases to 0, then we will push it into the queue and again process it similarly. Now, if the topo size, that is the number of nodes in our topo sort, is not equal to num courses, that is total number of vectors, then we'll return the empty vector, because that means our topo sort could not be completed because there was a cycle in the graph. Otherwise, we'll return this. Means the answer. Is there any doubt in this?
No.
Okay. Any questions? Did you all understand or there are any questions? You can ask.
Understood.
Okay, good. Now, Surya, please continue with your questions. Surya, you there?
I think that discussion has already gone for too long. So let us end the class today.
Okay, if you have any doubt, you may ask or you may leave me. If do you have any doubt?
No, Bhaiya.
Okay, then you may leave.
Thank you, Bhaiya.